Perfect. Ready when you are.
Okay. So thanks very much for accepting the paper, and it's very good to be here 2 years after the first workshop. So the title of today's talk will be that these two regimes matter for the long run. And I like to start immediately with a motivating example that shows what I mean by the long run, and then the meaning of this question. So basically, if you think about you define the return of an asset between time t and t plus one, and you get this one period return. You can actually then define the long run return generally by over n periods by taking the cumulative product over this of the returns over this period. So that if you take just the plain return, the long run return over n periods is the accumulation of the one period return over this m horizon. And then if you go to, instead of just considering the plain returns, you consider the log returns, then you get that the log long run return is given by what? By the accumulation, the sum of the one period log returns over your horizon. So that basically the long run return will be the sum of the short run or one period return over your M periods, right? And then the question is that in empirical finance literature, there is ample evidence that there's one class of models which can really proxy well the behavior of stock returns, which is the Markov-Witting class of models, which accounts for this sort of bull and bear markets, this kind of business cycle dynamics, and it does so by having this latent chain ST. And so then the question of the paper is if the one period returns do actually have regimes, what happens to the long run returns? So that if the distribution of the one period return RT depends on regime ST, what happens to the accumulation of the returns when M increases, okay? So that will be the full scale of, so what we are studying is not just one M fixed, but it will be, let's say, as a function of M. So what happens as you accumulate returns over different, over a scale of long horizon, long run events. Okay, and then there's so in part this motivation of study this problem of long run distributions comes from the finance literature that in the recent years has witnessed this boom from these empirical guys like the usual suspects like Pham and French. And then there have been like many papers that like, for example, this Bessembinder paper was very famous because there are basically all these papers, they are studying the empirical properties of the long run returns, so that they go from asking, okay, we know pretty much how returns behave over 1 month, but what happens if we look at the returns over 10 years period, 20-year period, 50-year period? And then they make the case whether actually stocks are a good investment for these long horizons, whether they, for example, outperform treasury bills returns when you consider like, like this very long time span. And then there are also this contribution, more theoretical, by Mickey Chernow at UCLA, where he's looking at asset pricing restrictions. But in econometrics, this is actually a very old question. It just goes under a different name, which is temporal aggregation. And it's actually very good being from UCSD because much of this work was done by Clive Granger. And then, so for us, econometricians should not be, surprising like that we are interested in this problem since much earlier than the empirical finance guys. Okay. So hoping that was enough to be interested in the second part of the talk, we now move to the setup and the results of what we actually do in this specific paper. So the setup I'm going to consider is very, very simple. So I'm going to take Markov-Witting VAR, so will be a vector autoregressive of the first order that will display this regime switching behavior. So this VAR we'll actually have that the parameters will be time varying, and will be time varying in a very specific way with this latent chain ST, which is a Markov process of the first order. Okay, and then what I'm going to do is that from now on, I'm going to refer to YT, just plain YT, as the short run process. So this guy can actually, you can think about it in terms of frequency as 1 day, 1 month, whatever you think your data frequency, your true data frequency is. Okay, so if you think your returns are actually generated at monthly frequency, then T is the short run is going to be monthly frequency, right? And then what we are going to treat as long run will be any sort of aggregate that you form from this short run process. So that if your true frequency is monthly and then you want to go, for example, 2 months, that will be a long run of 2 months. If you want to go yearly, that will be 12 months, basically aggregation, right? And this is will actually is forming the basis on how I'm going to treat this problem or solve it or study it, call it as you want. That will be, I'm going to study the long run properties of this Markov switching VAR class of models by temporal aggregation. So I'm going to try to be more finance guy by leveraging on my econometrics nature, and then answer this question about what happens to long run returns if you have regimes by like using this toolbox, which is that of temporal aggregation. Okay, so just a few remarks, because I've got backfired that, oh, that is a Markov switching VAR of first order, super simple process. But actually, that is what you need, because it actually, you can see that as a representation, so that is actually the companion form of a more complex model, like an MS with Varma model. And then it's n-dimensional, so you're actually not only one series is not scalar. You can have many series. You can actually have also predictability specifications, so that you can nest time varying predictability specifications. And so it's a very general class of models. So it's going to be MSVAR1, but what actually that guy is representing a whole class of Markov switching specifications. So it's a very rich setup. Okay, and so as I said, what I'm going to do is that I'm going to treat it as a problem of temporal aggregation, and to gain more generality, I'm not going to just focus on long run process as I define in the motivating example as the simple sum, for example, of the returns over some m period. But what I'm going to do is that I'm going to define through a general filter that governs the temporal aggregation. And so depending on the weight that you assign in the filter, you can actually get different temporal aggregation schemes. So that will be for different long run processes. So that will be a way to get more general results, but which can actually allow us to not only focus on what is called flow aggregation, but stock aggregation. So that if you have some process like log returns, then you get this clear link that the long run is just the sum of what happens during the short run. But if you have different kind of processes, then the long run is just a snapshot of the short run. So that, for example, if you think about prices, which are stock quantities, then prices do not aggregate over the long run as returns, for example, because returns are flow variables. So what you observe in the long run is the sum of what has happened in the short run, while prices are stock variables. So what actually you observe in the long run as prices is just the prices at that long run horizon. So at that long run instance, but it's definitely like something that, is a snapshot of the short run. And this way of solving this problem, treating it as a temporal aggregation problem, is actually allowing me to address all these points. Okay, and then the results. One key result is, we start from this short run Markov switching model. So the main question is, okay, once we aggregate, so we go to this long run. do we still have Markov switching dynamics? Are we still in this class of processes? And the answer is yes, and that is regardless of the aggregation scheme that you consider. So that whether you consider flow variables or stock variables, when you aggregate them, so when you go from the short to the long run process will still be in that class of models. So will still be a Markov switching model. Okay, and so this is what this slide is telling you, is that these models, as we will call them in econometrics, they are closed under temporal aggregation. So no matter how you aggregate them, you end up in that class of models. Okay, the parameters will be different, but you are still in that same class of models. Okay, and then of course there is just one thing then about the functional specification. Then we want to know what happens to the stochastic properties, because it might be that you are still in the same class of models, but the stochastic properties change, or for example, the nature of regime, as it actually will be the case, will change. So these are all things that we need to ensure and shed light on. So the first other thing is whether the stochastic properties are maintained, and the answer is again yes. So that if your short run Markov switching model is stationary and ergodic, then that holds true for the long run process as well. And so that allows us, to do inference, get consistent estimators, and all those sort of things that we really need to make inference and draw conclusions. But then there's also, and I think this is one very interesting thing, point on what happens on the very long run, right? Because maybe I tricked a bit you in the sense that when I talk about long run, you would have expected, this guy's going to talk about what happens in returns over 800 years, right? But that was not the case, but I can show you what should happen in the very long run, which is what happens when you take your your aggregation frequency, and you push it to infinity, so that you will consider really log return, the long run return over, since Jesus Christ age. And that I call it the very long run process. And what this result is saying is that in the very long run, actually regimes disappear. Well, this is not surprising, because it's something that is coming. If you look at the gauge literature, for example, it's true there as well, that when you have a gauge and you aggregate the gauge over the long run, like over these very long periods, the conditional heteroscedasticity disappear. Okay, and so this result is exactly equivalent to that, but in the case of regime switching, right? And then there's point what happens to the Markov chain. What happens there is that the number of regimes is actually changing, so the structure of the chain is changing as you aggregate. So the nice thing is that the ergodicity of the Markov chain is preserved in the aggregation, but the not so nice thing is that the number of regime is growing. And the thing is that the good but bad thing, the good thing, because it allows us, it shows that these results are important to understand how these Markov switching dynamics unfold at different frequencies, is that it's true, in the long run, in the aggregated process, you will still have regimes. But the problem is that this number of regimes that you have is actually increasing, is compounding, when the probability of visiting these regimes is getting weaker. So that since the aggregated regimes are given by the combination of the short-run regimes, the probability of visiting these regimes is also given by this combination of the short-run probabilities of being in each regime, so that you have this regime path, and then it comes to be, what's the probability of being in one of these regime paths, and those probability will be very low. So why that is bad because it will have very it will imply difficulties in identification of these aggregated regimes. So that if you go to long run processes and you will have in the empirics fewer data points, then grasping what is the state space of the regimes will be very difficult. So that if you, for example, want to identify regimes from data which are aggregated at quarterly frequency, for example, consumption, then that will be very difficult. So the regimes that you will observe regimes, but will be a misclassification of the true regimes that you have, which is what we see in the, I think, in the, consumption asset pricing literature puzzle, is one thing that might happen there. No, and then in the paper, of course, to corroborate this thing, I do simulation study, empirics. So starting from the simulation study, what I do there is that, in there you can play and have long run processes with many observations. And that is what I do in the simulations. I simulate a scale of different frequencies that we might be interested in. So for example, I start from daily, saying like the short run process is daily, and then I consider few series like weekly, monthly, up to 180 sort of days, which will be 6 months period. And then I go in with the class, the MS-VAR process, and I try to see what is the number of regime implied with a reasonable number, like 2,000, 2,500 observations. And what you actually see is, as I said, that the number of regimes that you should have is actually increasing. You still don't pick up, k to the power m regimes, because you need crazy amount of data to do that. But still, you see that the number of regimes is actually increasing, right? Which is what the theoretical results suggest. And then I try to go and also have an empirical thing that mimics again this simulation. But a problem with empirics is that you cannot actually have long, massive, long return, long series at the aggregate horizons. And so there, I start from daily data with 13,000 of observation. I take a series of returns on S&P 500, the Nikkei, so that is a bivariate VAR of 2 dimensions. And then I aggregate them. So these are log returns. So you sum them and you get the long run processes, and I aggregate them till biannual frequencies. And then I go in and I try again to estimate the number of regimes from this Markov-Switching VAR1 on these empirical data. And what I actually see is the opposite pattern, meaning that as you actually increase the frequency, you observe fewer regimes. And of course, there one of the issue might be that you have few data points, so you cannot expect to really identify many regimes with so few data points. But the thing is that, as I was saying in the discussion of the implications, is that these regimes, as you aggregate, they get weaker. And so the problem there is really this identification, because you have two things. You have weaker regimes and fewer data points. And so then you are really like going to be in bed, in high waters. Okay, and then to the conclusions. So do regimes matter for the long run? Well, the answer is yes, but to a lesser extent. And that also depends on how long is the long run, because I showed you that actually the long run can be 5 days, or it can be 800 years. And so there is really a key of, what's the frequency of your data, and what do you believe the data frequency of the DGP is actually is. Okay, I'm going to stop here to see if you have questions.